So let's take this now. We have to enforce boundary conditions to deal with those constants. So moving on here to the next page. There's our solution that we just identified. So now let's identify the boundary conditions. Up here we have, for our extended surface, let's say that the base is at TB, at the base of the fin, and it's directly attached, so we can assume that the base of the fin is at TB. Again, for your homework, that's not necessarily true. You'll have another thing to deal with. Second boundary condition out here at x equals L is going to be that q dot's 0. Right? That's our second boundary condition. So again, don't confuse that there's the convection part of it, but the boundary conditions have to be in the domain that we're modeling in x. So okay, let's come up with expressions for these two things. First is to say, for boundary condition 1, t at x equals 0 is equal to tb. Right? And if we're going to enforce that, what we need to do is take our general solution, which is, let's see, where am I over here? Which is the C1 cosh of m times x, but we're at x equals 0, so let's say m times 0 plus C2 sinh of m times 0 plus t infinity has to equal tb, right? That's the statement of our boundary condition using our general solution. Okay, so let's see. Cosh of 0 becomes 1. This becomes 0. So what this is saying then is that C1 is equal to TB minus T infinity. Great. So we have our first boundary condition, our first unknown coefficient, unknown constant. Second boundary condition is going to be that heat flux boundary condition. So let's do that. What we're saying there is that dt dx at x equals L equals 0, or right, it's just q dot equals 0. So let's plug in our temperature solution there. And we end up with, let's see. So first let's compute what dt dx is. So dt dx is going to be C1 m sinh of m times x, but let's evaluate it at L, plus C2 m cosh of m times L, all of that equals 0. So remember the hyperbolics, sine and cosine, they don't flip signs when you take the derivative. So derivative of cosh is sinh, positive sinh, and vice versa. Right, so that's our evaluated condition for our boundary condition. So what? So we can now solve that to get our value of C2. So rearranging this, we just end up with C2 is equal to minus C1 times sinh of ml over cosh of ml, which is equal to minus C1 tanh of ml. All right, so now we have, you could substitute C1 back into that, but we have our complete solution, right? We have the general solution for temperature, and we have two expressions for C1 and C2 that we can then plug into E's or whatever we want to do. So this problem is like general enough or seen commonly enough that people continue on with this and non-dimensionalize it and make it into useful forms and put it in tables. So let's go a little bit further on this so we can just kind of see where that all ends up. So the first thing we want to do is take our expression for temperature and non-dimensionalize it in terms of like a normalized temperature. Right? If we look back at this plot, we will be doing something like this, where we want everything in terms of this temperature that goes from 0 to 1. So when it comes to actually solving a problem, you can do it for any temperature range. Okay, so let's do that. You end up with this expression here, which is, let's see if I do this without running out of room. T minus T infinity over T B minus T infinity is equal to cosh of M times L times X over L. Okay, so what did I do there? I want to do this in terms of non-dimensional, so it's M times X, but I'm also multiplying by L over L, just so I can get this X over L term in there. Okay, so we have that cosh appearing there, and then we have minus tanh of ML times sinh of, again, ML times X over L. Okay, so this expression is now entirely in terms of non-dimensionalized. What I did was I took the C1, substituted in here, put C2 in the original equation, and then rearranged it to look like this. So hopefully the algebra is all right there. But we have this normalized equation. So we can keep going a little bit further. And there's an expression I wrote out. Hopefully you got it correct. Go a little bit further, and let's now plot this solution in terms of different ML parameters. Right, remember, M is that set of constants multiplying the temperature terms. If we take M times L, which is the length of the fin, and plot it out, we get this family of curves. Right? This looks a lot like that plot that we had before, where you have, for really low values of ML, all right, again, let me just write out what M is. So ML is equal to the square root of a parameter times H over KAC times L. So what I'm saying here is, let's look at a small value of ML. A small value of ML would be something like really high conductivity or really short length L. In that situation, it makes sense that you would have the entire temperature of the fin be pretty close to 1. Right? It's really not losing that much heat. Conversely, if it's the other way around, really low conductivity, for example, all that heat's going to be lost right away before you get too far along the fin. So the point here is that we went through this solution, but you came up with this family of curves that if I have a fin, rectangular fin, or constant cross-sectional area fin, that has an adiabatic tip and the base is at TB, this is valid, like universally. Right? So you've done this once, now you can put this table in your folder, and when somebody asks you 20 years what the fin performance is going to be, you just pull this out. Right? You don't have to do it again. So this is the way that people normally will express the results of this kind of analysis. Okay, any questions on that part? Okay.
So what is a constant base temperature actually a good assumption, though?
So it would be a good assumption if you have like an extended surface that's actually like welded to the base metal or something like that, right? If you have, you'll see in the homework, if you look at like fin heat exchangers, like if you go into your refrigerator, open it up, take it apart, and look at it, this is why you get the homework, because I had to do this. My fridge stopped working, and I was laying in a puddle of water thinking, how do I solve this with ODEs? So if you go look, the fins are like kind of loosely attached to the tubing, and there you're going to have a contact resistance. So it just depends on like the type of system you have. Like for a computer cooling heat sink, that's almost always like a base that's actually like cast with fins on it. So that's where it would be a good assumption.